In this video, I'm gonna briefly walk you through how to start building on bSquare network. It is basically the same as how you would do on other EVM-compatible chains. So if you are already familiar with this kind of stuff, you can just skip the video and get right on hacking. For beginners, the general workflow may include following aspects. I'll just dabble in a few of them today, and here is just to give you a rough idea. Firstly, there are some technical choices you should probably keep in mind. For instance, what's the smart contract language you plan to use? Beginners should probably just go for Solidity, because it simply has way more learning resources and broader ecosystem. You should probably keep up a framework to work with, which may help you streamline various development tasks. Meanwhile, ballpark of your time will be spent on designing, implementing, and testing your smart contracts, like unit testing, integration testing, and probably some invariant testing as well. In addition, to improve user experience, you may also consider setting up some event syncing services to aggregate on-chain data for the front end to consume. And finally, the front end will interact with the contracts via API. It's also a good idea to integrate account abstraction into your dApp. In our case, since we partnered with the Particle Network, you can simply integrate their BTC Connect SDK in order to onboard users with BTC Wallet directly. Now to start with, a couple of frameworks to choose from. Hardhat is usually a good place to start with for JavaScript or TypeScript developers. As you gain more experience, you may start tapping into Foundry as well, which provides many advanced features, such as fuzzy testing and EVM cheat codes, enabling you to write tests and scripts directly in Solidity without the hassle of context switching. For the remainder of this video, I'm just gonna stick with Hardhat. Now let's move on to scaffolding our new project. Here I'm using Yarn as my package manager, install Hardhat as dev dependency, run Hardhat any command, and choose TypeScript with VN as the template. Then we'll arrive at this project structure, where you'll have a contract folder containing a sample log contract, an ignition folder containing deployment scripts, which we'll cover later in the video. Meanwhile, testing scripts are located in the test folder. The next thing we'd like to do is to modify the Hardhat config. Firstly, that's after the Solidity entry, we will simply add optimizer settings. Then we'll add network entries, where we configure obvious settings for bSquare network and testnet. Also the EtherScan entry used for contract verification. And optionally, you can also install .env or .envflow package so that you can maintain secrets locally in .env files and load it up into your application. Now let's have a look at how to deploy it with Hardhat. There are primarily three ways to do it. In the old days, we either write vanilla Hardhat scripts with a runtime API, or use Hardhat deploy plugin to track deployment states for us. Both of these two ways are imperative, meaning that it usually takes us extra efforts to really make it robust and idempotent. More recently, Hardhat introduced their own declarative deployment system called Ignition, aiming to solve many of these pain points. The core concepts to get yourself started in Hardhat Ignition are module and future. Module is composed of futures which represent the result of execution steps. There are different kinds of futures predefined corresponding to different intended actions. The most common one is contracts, corresponding a transaction of contract deployment. One of the highlights is that Ignition will manage dependencies among these futures implicitly for you, so that we don't have to give too much thought about the exact order of transactions as in imperative ways. Another considerate design is that deployment-related parameters are actually decoupled from deploying logics and maintaining separate JSON files, which improves reusability greatly. In this example, I deploy two contracts, lock and lock v1 with contract features. Read unlock time property from v1 with that call feature, and deposit into v2 with call feature. Now let's see this in action. Here I'm just gonna grab a simple contract, modify it a bit, and make sure all the tests have passed. Do remember to update your private key in the .env file. Here is the module definition we've mentioned earlier. Let's modify the initial locked amount. Now we can just execute the deploy command. To verify our newly deployed contracts, we also have some options here. You can verify manually on our Explorer interface, which may cause a bit of hassle if you have many contracts. It can make our life easier by using a plugin like Verify that automates the process for us. More conveniently, since Ignition already have this plugin baked in, we can either do it with deploy subcommand by adding verify flag, or separately with verify subcommand. Now we can see our contract has been verified. That wraps up today's video, and thanks for watching.
We're going to go through the process of building a demo application that implements BTC Connect within B Squared, onboards a user through their Unisat, OKX, or BitGet wallet, and executes both a smart account transaction on B Squared and a native Bitcoin transaction. So let's jump right into it. As I mentioned, today we're going to be building one main application. The goal of this application will be to basically showcase what the integration flow of BTC Connect looks like in B Squared. It's pretty simple. All we're going to do is basically onboard a user through the wallet of their choice. In this case, we'll let them choose between OKX, BitGet, or Unisat. Then once they've logged in, they'll be able to see both their Bitcoin native balance and their EVM balance. Then they'll be able to do two transactions. The first will be a standard burn transaction on B Squared, just to showcase the functionality. And the second will be, again, a sample transaction, but on Bitcoin native to showcase the functionality there. And both of these transactions will actually happen through the same wallet interface due to the nature of BTC Connect, with the latter transaction being gasless because, of course, it's using a smart account that we're sponsoring the gas fees on. So in this video, like most of our videos, we're going to be using a basic create React app structure for the application, meaning we're going to be working out of two files primarily, app.tsx and index.tsx. Of course, you can do this in JavaScript too. If you want to do .jsx, that would work. But in this case, we're going to be using TypeScript, with the index file being used for configuration and the app file being used for our core application logic. So to get started, let's actually begin in the index file to configure the BTC Connect SDK. Essentially, BTC Connect is configured through a component called Connect Provider. We'll take various different parameters, including some required and optional ones. Then it'll wrap our core component for our app.tsx file, therefore allowing us to use BTC Connect within app.tsx through the configuration that we're setting here. So to get started, let's first import a few different base libraries. The first will be React from React, and the second will be React DOM from React-DOM/client. Then we can import some objects from two different particle-related libraries. The first, of course, will be BTC Connect, in which we'll need to import four main objects, starting with Connect Provider. And for the wallets it will support, we can import OKX connector, Unisat connector, and BitGet connector. That'll be from appparticle-network/BTC Connect Kit. Then additionally, we can go ahead and import the B Squared testnet from appparticle-network/chains. Then to close it off here, we can import app from ./app, or of course the equivalent for the component that you want to be using BTC Connect within. Okay, so to go and get started, let's call React dom.create root, and then pass in document.get element by ID, which will take root. Then we can go and cast that to HTML element and call the .render method. Now let's go and open up a React strict mode. And within here, we can open connect provider. Now connect provider will basically take two groups of configurations. The first of those two groups will be options. Options will contain the configuration for our optional embedded wallet modal, as well as the chain that we want to use within BTC Connect. And finally, what we're going to start with here, 3 required values that we need to connect our project with the Particle dashboard. So every Particle SDK that you use is going to require 3 values to be initialized. This is your project ID, your client key, and your app ID. Collectively, these values basically connect your project with the Particle dashboard, therefore authenticating API requests, tracking users, allowing you to fund your paymaster, etc. So in this case, before we start with the options property here, first head over to the Particle dashboard and create a new project. All right, so we're now here on the Particle dashboard. So let's go and click on Add New Project, and I'll name this B squared demo, then click Save. Now within here, as you can see, we already have our project ID and client key, but we'll also need our app ID. Although before doing that, as you can see, there's a lot here on the dashboard. Beyond just getting the 3 keys here, you can check the activity of your application, the specific users using your application, fund your paymaster for gasless transactions, and so on. But sticking to the applications menu here, let's go ahead and create a new web app right here and name this again B squared demo. And then also throw in the domain in which you're hosting your application right here. Although if you don't have that just yet, feel free to use any filler domain such as google.com or something like that, and it'll still work. Then go ahead and click on OK. All right, so let's now copy the project ID, the client key, and the app ID. We can now throw those into environment variables within our application and move on. So starting with those 3 values, let's go and define project ID as process.env.react app project ID. And we can do the same thing for client key as well as for app ID. Now beyond these 3 values, let's also go ahead and define AA options. Then within AA options, we can define account contracts, which will contain BTC. And then within this BTC array right here, we can essentially define what chains we want to use within BTC Connect. So we can set chain IDs to b squared testnet.id, as well as the version to 1.0.0. The version doesn't really matter right now, but feel free to always set it as version 1. And then additionally, we can customize the optional embedded wallet interface, because essentially whenever a user connects to your application using their Unisat or their BitGet or OKX, then you're basically generating an EVM-based smart account for them to use through their native Bitcoin wallet. So you can optionally give them an embedded interface that provides a MetaMask-like way to work with that smart account directly rather than just using your application. This is a good option if you expect your users to create and use their wallet exclusively within your application, in which you can set wallet options and then visible to true. Although of course, if you don't want that within your application and just want to rely on the actual functions of your application to interact with the smart account, then feel free to set this as false. Now connectors will contain basically an array of wallet objects that we want to be supported within BTC Connect. So let's start with new Unisat connector, the new OKX connector, as well as new BitGet connector. Of course, if you only want to support one of these or 2 of them, then feel free to select which ones you want and use them accordingly. With that being closed out, let's also go and throw in our app component right here. We're now done configuring BTC Connect. As you can see, we imported a number of base libraries. We used our project ID, client key, and app ID from the Particle dashboard to initialize the SDK. We configured our smart account and ensured that the embedded wallet for the smart account is visible. And finally, we set the different wallets that we want to be supported within the connection mechanism right here. So let's now move on to app.tsx. As I mentioned, app.tsx is going to be used for all of our core application level logic. So the process of actually onboarding user into the application through their wallet connection, pulling their balances, executing transactions, displaying all of this within the front end, etc. In this example, it'll be about 120 lines of code, but of course, depending on how you're working with this, it can be much less, but we're going to try to be pretty comprehensive here. So let's go and get started by again importing a few different base libraries. So we'll start with React alongside useState and useEffect. Now for the second import here, it's important to establish the main mechanism in which BTC Connect operates. Essentially, BTC Connect is mostly used through hooks. Specifically, in this case, we're going to be using 3 hooks, which will be use ETH provider, use BTC provider, and use connect modal. Collectively, these 3 hooks will allow us to define around 7 different functions and objects that we'll be using throughout this application. So then this will come from @particle-network/BTC connect kit. To make our usage of account abstraction of the smart account a little bit easier, let's also import a wrap provider and send transaction mode from @particle-network/AA. Let's also import ethers as well as notification from AMD. We can close it out by importing our CSS. All right, cool. You can ignore some of this stuff, just some front-end components not important to the underlying application. But what we just did up here is that we imported various different libraries that we'll be using in a moment for our entire range of functionality. So to start doing that, let's go ahead and open up our main app component that I referenced earlier. We can call this app, and starting within app, let's define some functions derived from the 3 hooks that we just imported. So let's start with smart account from use ETH provider, and then open connect modal and disconnect from use connect modal. And finally, we can do accounts, then send Bitcoin alongside get network from use BTC provider. In addition to these, let's also set 3 states, starting with address and set address as use state and then null, and then balance EVM and set balance EVM, also as use state and then null. And finally balance BTC and set balance BTC. So starting within our application here, first thing that we want to do is create a custom ethers provider that we'll be using to do things like retrieve the EVM balance, send transactions, etc. So we can construct this provider within custom provider and new ethers.providers.web3 provider. And as we just imported, pass in a new instance of AA wrap provider, which will create a custom 1193 account abstraction enabled provider object that we can use to drive interaction through our smart account within Ethers. So within AA wrap provider, let's pass in smart account, as well as send transaction mode.gasless, which will essentially request a gas sponsorship for every transaction that we send through custom provider. This means that if you're on a testnet, every transaction that you send will be gasless, or if you're on mainnet, it'll either sponsor it if you have enough funds in your paymaster, or it'll undergo a conditional that you set on the particle dashboard. Okay, so to close this off, let's also do any. All right, so the actual application here is going to be separated into basically 4 core components. The first will be pulling the user's address, as well as their EVM balance and BTC balance. Then we'll handle the actual wallet connection component, so allowing them to connect their wallet with the application. Then we can build out 2 functions, the first being execute TX EVM, which will send a gasless burn of a small amount of BTC through the smart account. Then we'll do a second transaction for transferring 1 Satoshi on native Bitcoin. So let's first start with the address and balance retrieval through opening a use effect. And essentially within this use effect, we want to wrap all this within a conditional that checks if accounts.length is greater than 0. By doing this, we're basically ensuring that this use effect does not get executed if the user has not already logged in. So if accounts.length is greater than 0, then we know for sure that the user has already connected their wallet and therefore signed in. Otherwise, if they haven't, then accounts.length will be 0, and therefore the logic within this use effect won't be executed. So assuming that the user has connected, we can go and define pull account info as asynchronous. And then within here, let's start by defining the address as a DDR, then await smart account .get address. Then we can set that address with set address, passing in a DDR. Now we also want to pull the EVM balance and the BTC balance. So starting with the EVM balance, let's define balance response as await custom provider .get balance and pass in a DDR. Then we can do set balance EVM with ethers.utils.format ether, passing in balance response. Now the reason we need to do format ether is because by default, balance response is going to be in a WAV format, which isn't very readable. So we're converting it to the standard ether format right here through ethers.utils. All right, now fetching the Bitcoin balance will be a little bit more complicated because we basically need to call an API and essentially dynamically generate a request based upon number 1, if we're connected to the Bitcoin mainnet or testnet, and then 2, of course, passing in our Bitcoin address through the accounts array. So let's go and do this within fetch. Then we can pass in this API right here. Now right here, we need to basically determine the user is connected to the Bitcoin mainnet or Bitcoin testnet so that we know what network to retrieve the balance on. So let's do await get network and check if the response of that is livenet. If it is, then we can pass in main. Otherwise, if it's not, so if it's the testnet, then we can pass in test3. So this will ensure that the URL is constructed based upon the actual network that the user is connected to. Then we can do /addrs and pass in accounts and then 0. And finally, we can do /balance. Then call .then, do the response, do r.json, then call .then on that. And pulling data, we can call set balance BTC and pass in data.balance by 28. And there we go. So essentially what we're doing here is calling the block cipher API based upon whether we're connected to the mainnet or testnet and setting the balance of BTC, making sure that we convert it to a standard format, similar to what we did with format ether, but of course it's manual in this case. Then we can go and call pull account info and make this use effect dependent upon the state of accounts and smart account. Okay, so now we have a mechanism for pulling the user's address as well as their balance on EVM and on BTC. So let's go and build the other 3 functions, starting with the handling of wallet connection. So wallet connection with BTC Connect is very simple. We're basically just going to be wrapping the open_connect modal function within a conditional that makes sure that the user is not logged in. So let's define this within handle login, and within handle login, first check if accounts.length is truthy or falsy. So within this conditional, let's go and call open_connect modal, and that's it. That's our entire wallet connection functionality in about 5 lines of code. So now for the latter 2 functions. Once again, this will be 2 transactions, the first being a burn of a small amount of BTC on the B2 network. Then the second will be a sample transaction on the Bitcoin layer 1, transferring 1 sats to myself. Let's go and define execute TX EVM. That'll be asynchronous. And to open it up, let's first go and define our signer through custom provider.get signer. We'll be using this in a moment to send the transaction, but beforehand, let's go and define our actual transaction object within TX. If you've used Ethers or Web3.js or any other standard framework before, then you're probably familiar with the structure. We're basically going to be doing the same thing as you would on any other network within any other account by simply defining things like to, and in our case, because we're doing a burn, we can set this data address right here. Then we can set the value as ethers.utils.parse ether, passing in 0.000001, as well as data as 0x. Although, of course, if you're calling a contract or anything of that nature, then you can populate data. But for now, because we're just doing a burn, we can leave that as 0x. So pretty standard. This transaction will actually automatically be converted to a user operation by our account abstraction enabled provider, and therefore can be formatted and executed through the same mechanism that you're already familiar with, and of course, directly through the smart account attached to the Bitcoin wallet. So now to actually execute this transaction, let's define tx response as await signer.send transaction and then tx. Now this will actually request the wallet to confirm the transaction, the EVM transaction. And then once they do so, it'll be pushed to the B-squared testnet and of course settled. Although let's do one more thing, which is retrieving the transaction hash to actually display to the user, indicating that the transaction was successful. So let's define tx receipt as await response.wait and then call notification.success, setting the message as transaction successful and the description to transaction hash and then tx receipt dot transaction hash. Usually what we do here is actually embed an Explorer link into this notification pop-up, but the B-squared testnet Explorer is a little bit behind, so it actually wouldn't show up on the Explorer. Therefore, we're just going to go the simple route and display the transaction hash directly to the user. All right, so that's our execute tx EVM function complete. That will send a gasless burn transaction on the B-squared testnet. Let's now do a somewhat simpler function for executing a sample transaction on the Bitcoin layer 1, of course to the account attached to the Bitcoin wallet that the user connected with. So let's do execute tx BTC. That'll again be asynchronous. Now this can basically be done in one line of code. We can define this within hash and call await send Bitcoin, then pass in accounts 0 as the recipient. Of course, you probably actually want a real recipient here, so an address that you or the user would define. But for the sake of this example, we're just going to send the Satoshi back to ourselves through passing in account 0. Then of course we can actually define the value as the second parameter, which is denominated in Satoshis. In my case, it'll just be 1. Then optionally as the third parameter, you can set the fee rate for the gas fees, but we're just gonna leave it as is for now, sending 1 Satoshi back to the sender. And that's it. Upon calling that, the user will be requested to sign the transaction, then it'll be executed on chain. But let's also go ahead and throw a notification.success with once again the message as transaction successful and the description to this right here. Basically all we're doing is displaying the transaction hash, but attaching a link to it, which will take us directly to the block cipher explorer, showcasing the transaction in question. And that's it. At this point, we've imported a number of base libraries, defined all of our hooks, defined some states, constructed a custom ethers provider, pulled the user's address, EVM, and BTC balance, handled wallet connection, executed a gasless burn on the B-squared testnet, and sent a sample transaction on the standard Bitcoin chain. So let's now go and wrap all this up through formatting everything within our JSX. Let's open up a return statement. And within these videos, what we typically do is actually skip this part because it can take quite a lot of time and be a little bit repetitive. So I'm gonna get this written and then come back to explain it. So as you can see, it's pretty simple. We're basically checking if address is defined. So just another way of checking if the user has logged in or not. If the user has not logged in, so if address is undefined, then we're displaying the connect button right here. And once the user has logged in, we can display their BTC balance on the smart account within B squared, as well as that smart account address. And below that, we can show them their balance in BTC on the native layer 1 chain, as well as their native BTC address. Then of course, we're presenting them with 2 buttons, execute EVM transaction and execute BTC transaction. Then one final button for logging out, which just calls the disconnect function that we defined up here. So all we have left to do now is throw in export default and then app, and then go ahead and run it and see if it works. All right, so here we are, and it looks like it worked. So let's give it a try by clicking on connect. Then I'll go ahead and select my Unisat wallet right here and click on connect. And here we go. As you can see, I'm now connected to this application using BTC Connect, which is through 2 accounts. The first is the smart account directly tied to my Bitcoin wallet, and of course is the native Bitcoin account also tied to my wallet. And we can see the balances here for both. And of course, we can copy each address like this and use them later. Also, as you can see here in the top corner, I'm on the BTC testnet. If I go and switch to the live net, and as you can see, that switches, as does my balance. But let's go and stick to the testnet for now, like that, and take a look at the embedded wallet modal right here. Like I mentioned, because your Unisat, OKX, or Bitget wallet doesn't have a native way to handle and manage the smart account tied to that wallet, we have the option of you including this embedded wallet interface within your application. This will allow a user the same level of functionality that they have within their main wallet, but specifically tailored to the smart account attached to that wallet. Although, of course, this is optional if you don't want to allow the user to have access to that and just want them to use your application as is, then you can set that as false. But because we set this to true, as you can see, we have our balance in BTC, even have our USDC right here, NFTs, activity, send, receive, etc. But for now, let's go ahead and close this and try our 2 test buttons. Let's start with execute EVM transaction. Of course, this transaction is being executed through the smart account on the B squared network, and we're signing for it natively within Unisat, authenticating it with our account. So we can go and click on sign. And as you can see, the transaction was successful with the transaction hash right here. So let's try the same thing now, but for our BTC transaction with the second button. And as you can see, the same thing here, we're signing for the transaction within the same wallet interface. Of course, with this one being on the native Bitcoin network, the first one was on the EVM chain through the smart account on B squared. So we can go and click on sign and pay. And here's the transaction hash right here with the link to the transaction on block cipher right here.